Hey guys, welcome to the channel. This is the second episode and we are discussing some of the main ideas that you encounter in the chapter Motion Along a Straight Line. Now in the previous episode, we discussed position, displacement, average velocity and average speed. Let's begin this episode with the idea of instantaneous velocity. The instantaneous velocity v of a moving particle is v is equals to limit delta t tends to 0 delta x divided by delta t. Now this is nothing but dx by dt. What this is telling us is as you make the time interval delta t smaller and smaller, you reach a value that gives you the velocity at this instant of time. Hence the name instantaneous velocity. If you look at the graph of x versus t, the quantity delta x by delta t is the slope of this line, which is the average velocity. Now if you make delta t smaller and smaller by bringing t2 closer to t1, this straight line eventually becomes the tangent to the xt curve at this particular point. At this point, the slope is the tangent to the curve and it gives the instantaneous velocity. Now, another important point is that the instantaneous velocity is a vector quantity and the magnitude of this vector quantity gives you the speed. Now, this is the same speed that you see in the dashboard of a vehicle. The next big idea is the average acceleration. Average acceleration is the ratio of change in velocity delta v to the time interval delta t during which the change in velocity occurs. So mathematically, this is written as avg is equal to delta v divided by delta t. Here, the quantity avg is a vector quantity. Now, the algebraic sign indicates the direction of average acceleration. If the sign is positive, it means that the average acceleration of the particle is in the positive x direction. And if the sign is negative, that means that the average acceleration is in the negative x direction. So just like instantaneous velocity, we also have another quantity called as the instantaneous acceleration. Now instantaneous acceleration, or simply the acceleration, is the rate of change of velocity with respect to time. So A is dv by dt. If you know the velocity as a function of time, simply differentiating this function with time, you get the acceleration. We also know that the velocity itself is dx by dt. So acceleration is d by dt of dx by dt, which is written as d2x by dt2. So that means acceleration is the second derivative of the position function. So this is how acceleration, velocity and position, these three quantities are related to each other. The velocity is the first derivative of the position and the acceleration is the second derivative of the position function. If you think about this graphically, on a graph of v versus t, the acceleration a at any time t is the slope of the curve at the point that represents t. So in this graph, this line over here is the slope of the curve at this instant t. This slope is the acceleration. In other words, the tangent to the curve at a particular instant of time gives us the acceleration. Clear? Let us now solve a simple problem based on these ideas. So the problem at hand is the following. So given ahead is an xt plot for an elevator that is initially stationary. It then moves upwards, which we take as the positive direction of x, and then the elevator stops. Part A, plot v as a function of time. Part B, plot a, the acceleration, as a function of time. So I'm going to leave this question on the screen. You guys can pause the video and try it out. Let's begin with part A. The key idea here is that we can find the velocity at any time from the slope of the curve x of t. So the velocity is 0 in the interval from 0 to 1. And similarly, from 9 seconds onwards, the velocity is again 0. This is because the lift was initially stationary and then it came to a stop. During BC, the slope is constant and non-zero. So the lift moved with constant velocity. V is equal to delta x by delta t, which is 24 meter minus 4 meter divided by 8 second minus 3 second, and this is 4 meters per second. Now that the velocity is positive, this indicates that the lift is moving in the positive x direction. Now these intervals where the velocity is 0 and velocity is equals to 4 are plotted. In addition to this, the lift begins to move and then later comes to a stop. So V varies in the interval 1 to 3 seconds as follows, and then from 8 to 9 seconds the variation is as follows. So this plot that you see on your screen is the required velocity time plot for the motion of the lift. Now, using this velocity time plot, we can construct the acceleration time plot. This is what is to be done in part B of the question. So here is the Vt plot repeated again. In the interval 0 to 1 second, the acceleration is 0 because the velocity itself is 0. In the interval Bc, that is from 4 second to 8 second, the velocity is a constant. Its value is 4 meters per second. The slope is 0, so the acceleration is again 0. Similarly, past the 9 second mark, the slope is 0 here too. So A in this region is also 0. Now in the time interval 1 second to 3 second, the slope is rise over run, and that is 4 meters per second minus 0 meters per second divided by 3 second minus 1 second. And this is equal to 2 meters per second square. Notice that this is positive and a constant acceleration. Now in the time interval 8 to 9 second, the slope is rise over run, and that is 0 meters per second minus 4 meters per second divided by 9 second minus 8 second. If you do the calculation, this will be equal to minus 4 meters per second square. This is interesting. The acceleration is negative. That means the lift is in deceleration. It is slowing down. So if we plot all of this in a graph, we get the acceleration time graph. This completes the solution. At these time intervals here and here, the lift was in acceleration and deceleration respectively. Whereas over here, here and here, the acceleration is simply 0. The most important idea in this problem was that calculating the slope of xt graph at any instant of time gives us the velocity at that instant of time. Similarly, calculating the slope of Vt graph at any instant of time gives us the acceleration at that particular instant of time. So this completes the problem, and these were some of the main ideas regarding acceleration, instantaneous acceleration and instantaneous velocity. So I think this is a good time to stop. In the next episode, we will deal with ideas such as constant acceleration and free fall acceleration. In the meantime, keep practicing, and if you have any doubt, the comment section is always open. Thank you for watching the video.